Construction projects can have waste of more than 25%, caused by redundant documentation, unused materials, idle workers, and rework, among other factors. A significant portion can come from the building envelope and facade. Facade Design for Fabrication helps architects, engineers, and construction managers work more efficiently and productively with facade fabricators. Unlike most building information modeling technologies, Facade Design for Fabrication, powered by the 3D Experience platform, connects processes from end to end. Designers and engineers use a single integrated environment to produce designs, fabrication details, shop drawings, and assembly instructions. This video shows how a facade designer creates a concept for a new stadium, and a facade engineer produces shop drawings for manufacturing, all using a single 3D model in a seamless data environment. First, let's log into the 3D Experience platform. The facade designer creates an initial sketch of the stadium with CATIA using the 3D curve functionality. Freeform designs can be created using curves, polylines, complex surfaces, and solid geometries. Here, two curves are selected and combined. Individual segments of the curve can still be modified. Through the parametric design workflow, the designer can make changes based on customer requirements. This sketch shows vertical panels around the stadium. Let's watch the designer create a simplified representation of a single panel. The designer will replicate this panel around the entire stadium. The stadium has an irregular shape, so each individual panel needs to be adjusted to match the overall curve. The initial panel, with all of its design details, is registered as a user-defined feature. Now the user-defined panels are replicated around the stadium facade and aligned with the overall design curves. A knowledge pattern controls how a user-defined feature behaves throughout the model, including the total number to generate. The designer can simulate multiple patterns to determine which design plan works best. Here the designer enters 40 into the knowledge pattern, and we see that the stadium facade is divided into 40 different panels. Next, 60 panels are created. Finally, the facade model is divided into 100 panels. Even after the facade model has been partitioned, if changes are made to the initial wave curve, any resulting modifications are automatically applied to the affected panels. Our conceptual model is divided into upper and lower sides, both of which are divided into 100 vertical panels. The designer adds further detail to each panel. The upper panels are subdivided into varying numbers of plates. The designer specifies the maximum number of plates per panel at 4. As before, the designer selects one model to establish a template. Plate attributes and frame geometry are added to the initial panel. The dimensions of each frame are calculated automatically. Depending on the length of a given panel, it is divided into 2, 3, or 4 separate plates. For each of the 100 panels, we now have a total length, the number of plates, and the dimensions of each plate. This information will help the facade design team evaluate panel production quantities and costs. The designer exports all panel and plate data into a report to inform the initial quantity takeoff. The report can be exported into Microsoft Excel or HTML formats. The facade designer is now finished with the conceptual design phase. For the detailed design phase, a facade engineer continues to work with the stadium model on the 3D Experience platform on the cloud. The conceptual model created during the previous phase will serve as the skeleton for a more detailed model. First, the engineer creates an assembly for the panels. The skeleton drives the geometry and position of each part. Using a universal product template for a generic beam, the engineer can rapidly generate parts within the model. Each beam is generated as a unique part. Beam lengths are determined by the skeleton model. Parts can be modified individually or replicated at any time during the design process. Next, using CATIA, the engineer creates a sheet metal model, including thickness and folding details. The sheet metal model is placed in the assembly. Unfolded, side, and isometric views are associated with the part. The sheet metal model and its alternate views can be exported to seamlessly create shop drawings. The facade engineer will now create a basic assembly template. Registering the model as an assembly template allows other team members to reuse an assembly model efficiently. In the assembly template, the engineer can select which elements apply. Once the assembly template is created, the engineer runs a simple knowledgeware script. The script automatically generates each assembly around the stadium. The detailed design model is updated. It now includes 100 assemblies, each with unique parts as well as shared parts. To complete the detailed design, the engineer needs to add any missing parts. This can be done easily by selecting a standard part from the catalog and adding it to the assembly model catalog. And adding it to the assembly model. Because the 3D model is defined using an AEC data model, we can add IFC extensions to objects and see specific attributes for each product. Next, the engineer runs a predefined knowledge report to extract the data needed for part fabrication. The engineer exports valuable information needed for quantity takeoffs, generating the number of panels, the size of each panel, the number of beams, and other specifications directly from the model enables highly accurate cost predictions. In the end, each sheet metal panel has its own drawing. Each of these drawings can be exported in a DXF format with unfolded views that can be used for fabrication. This capability significantly helps the engineer with creating shop drawings. Once the detailed design is completed and ready for final review, the 3D model can be inspected from multiple viewpoints using CATIA. This allows the team to preview the stadium from various angles, better understand scale, and get the perspectives of multiple stakeholders. Facade Design for Fabrication fully supports the connected processes of creating conceptual designs, detailed designs, quantity takeoffs, shop drawings, and installation instructions for facades. For more information, visit www.3ds.com/AEC.